So this lesson deals with relative motion, which leads into something called projectile motion, which we're going to be spending at least 2 days on, plus a day for a lab. It's looking as though your unit exam in this unit will be Thursday of next week-ish, but as we get closer, I'll firm that date up. We're going to be solving problems where the object's motion is influenced by two different sources. So for example, if I'm swimming across a river and the river is flowing, if I start on one side of the river and I see my campsite on the other side of the river and I'm directly across from it and I start swimming towards my campsite, you know that I'm not going to reach my campsite because the river is going to take me downstream at the same time. We're going to just look at a different situation. This is not in your notes, but I've discovered that you need something maybe a little more concrete before we start talking about rivers or wind. So we have a small bug that is capable of walking with a speed of 7 centimeters per second. About that distance. There's the bug. If you can't see him, that's what he looks like, all right? Dumb as a box of rocks. Doesn't know what's going on in the world. This bug is just on a mission to walk 7 centimeters per second in whatever direction will take it to the food quickest, okay? And the bug starts walking from one end of a mechanical walkway at the airport as shown below. Everybody, I hope, is familiar with what I'm talking about. It's a moving sidewalk, right? We used to call them moving sidewalks. It's this big loop of some kind of synthetic material that's got 2 rollers on each end and a bunch of supports, and it just rolls around. It's like what you would see on a treadmill, okay? Except it's very long. The walkway is 9.9 meters long. So first of all, we need to appreciate that if we're going to be talking about the bug's motion in centimeters per second and the walkway is 9.9 meters long, that's 990 centimeters. If we multiply that by 100, by 10, it's, yeah, 990. 9.9 times 100. Okay. But it's moving very slow. There's something wrong with the motors in the walkway, and it's only moving at 2 centimeters per second, which means you might as well not even get on it if you're a human being, right? You're just going very, very slow. Slower than those little cars that you did that lab with. All right, so the question is, the walkway is moving at 2 centimeters per second. The bug is walking on the walkway at 7 centimeters per second, and the walkway is 990 centimeters long. How long does it take the bug to reach the end of the walkway? Why don't everybody try to figure that out? You've got a calculator. Although I think if you're good with numbers, you may not need a calculator. I want you to keep in mind that the bug is making up 7 centimeters per second of walkway, but the walkway is helping the bug out as well, right? The bug is actually going to be moving faster. If I were standing here, watching this little creature, sitting there drinking my coffee and reading my book, waiting for my flight that's not due for another 4 hours, and I watch that bug, he, she, it is not going to pass me at 7 centimeters per second. How fast will it pass me? 9. At 9 centimeters per second. This is what I mean by relative motion. The bug is looking down at the walkway and he's saying, well, I'm moving at 7 centimeters per second. But we're looking at the bug and the bug is moving at 9 centimeters per second. Well, we can use a speed equals distance over time situation. I don't need to worry about vectors here. The time will be equal to the distance the bug has to travel divided by how quickly it's covering that distance. So we're going to get 990 centimeters divided by the speed, which is 9 centimeters per second. I think that's 110 seconds. Okay? So there's a lesson to be learned here. And the lesson is, when you are moving on an object or through a material that's moving in the same direction you're moving, your velocity is actually a sum of your personal velocity plus the velocity of what you're moving in. So if this were a river, that was moving at 2 meters per second east, and my boat throttled forward at 7 meters per second, I would be going past the shore at 9 meters per second. All right, let's take a look at another situation. And again, this is not in your notes. The bug gets to the other side, has its lunch, has a little snooze, a little nap after dinner, and says, well, I got to get back home to the kids. So the bug turns around and starts going in the opposite direction. The bug is going to walk over the walkway at 7 centimeters per second, but the walkway is pushing the bug back, so to speak, at 2 centimeters per second. In other words, if you think about what happens in a 1 second time interval, the bug will have put 7 centimeters of walkway behind it, but the walkway itself will have moved backwards at 2. Which means every second, the bug's only gaining 5. And this is not an intelligent bug. The bug's wondering why it's taking longer to get home. But we know, because we're smarter than this bug, that what's happening here is when we use speed equals distance over time, and time equals distance over speed, we're going to still have that 990 centimeters per second, 990 centimeters, but this time we're only going to divide by 5 centimeters per second. Because the walkway is moving the bug in the opposite direction to the way the bug wants to move, what we're learning here is the velocity of the bug relative to the walkway is 7 centimeters per second, but the velocity or speed relative to us out here watching it will only be 5 centimeters per second. Again, I don't care about direction. I keep saying velocity, but the speed of the bug. We'll get to the velocity aspect in a second. So we divide these two. You get 198? Is that right? So it's 198 seconds. Any questions so far? This is not in your handout. It's just kind of a thought experiment to get us warmed up to what's coming. All right. What's the bug up to now? I don't know why. The bug doesn't maybe know why. The walkway is moving at 2 centimeters per second. The bug settles down over here for a nap, and then he sees something. A little spider or something, or just a piece of fluff, and it's attracted. So it walks straight across the walkway to that point. The first question is, where will the bug be when it reaches the other side? That's a difficult question. And if you can wrap your head around this question, you've got this lesson beat. First of all, would you agree the bug will not be here? Yeah? Would you agree the bug is going to be further to the right in the diagram? Do you think it's reasonable to say the bug will be here? And there's a reason why you should be able to answer this. Yeah? It's tough, isn't it? It's not a simple thing. The reason why you should be able to answer this is only going to be accomplished with calculations. Let me ask a different question. Wherever the bug lands, how long will it take this bug to reach the other side? So it's a good puzzle. So let's start with that. Let's start with a simpler question. Time to get across. And I know I'm going to get a number of different answers here, but I would like you to grab your calculator and see if you can figure that out. By the way, I've given you the width of the walkway. It's 104. I hope you would agree that if the walkway is wider, it's going to take the bug longer, no matter what. So I want you to see if you can figure out how many seconds it takes the bug to get to the other side. Remember, the bug is focused on the walkway. The walkway that's underneath its 14 feet, or whatever number that is. The bug doesn't know the walkway is moving to the right. How many of you are confident you have a number of seconds it takes to reach the other side? Noah, what do you think? 20. It is 20 seconds. And what Noah said, did you actually calculate it, or did you just look at the numbers? Okay. What Noah said is the bug is moving in the downward direction at 7 centimeters per second, and it has to move 140 centimeters in that direction. If you wanted to use a formula you're using speed equals distance over time, and let me cut to the chase now. The reason why we're going to put 140 in for D and 7 in for V is these are both y components of its motion. If you want to find out how long it takes to move 140 centimeters in the y direction, you have to use the speed in the y direction. So when we put those numbers in, you get the speed, which is 7 centimeters per second, I'll put the units in, equals 140 centimeters over the time. Take the 140 centimeters divided by the 7 centimeters per second. It takes 20 seconds to accomplish that. Now, unbeknownst to the bug has also been moving that way for 20 seconds. So now that we know it's a 20-second journey, and let's be clear, the bug doesn't do this. The bug doesn't go across and then down. It's happening at the same time. Okay. Now that we know it's 20 seconds that way, what we can do is say speed equals distance over time. But let's talk about the horizontal speed and the horizontal distance. The time is the same. If it's 200 seconds to reach the other side, it's moving vertically for, I said 200, didn't I? If it's 20 seconds to reach the other side, then it's moving vertically for 20 seconds, and it's moving horizontally for 20 seconds. There aren't two bugs, it's one bug. So that means we can put the 2 centimeters per second here. And the time of 20 seconds multiply and get 40 centimeters. You okay with that? How many of you knew, so it's going to be 40 centimeters this way. How many of you knew that when I put this here, that would be moving it too far in that direction? Why? Oh, and based on what would you think it was moving too far horizontally in this case?
It is moving much slower than it is downward, and it's thinner. The width is thinner than the length.
Yeah. And in fact, we can forget about the width and the length, and if I add, I know I'm getting a little bit ahead of myself, but if I add these two velocity vectors together, this will be the path of the bug. It's going to, we're going to be adding vectors together, but they're not displacements, they're velocities. All right. Let's get to the formal part of this lesson. And I think by doing what I've done with that kind of off-the-cuff example, I think it will be helpful as we go through these. I don't think we need to spend as much time on this as we would have normally had to do. A boat with an engine speed of 4 meters per second. This is what I'm going to call the speed of a boat if it were in still water. So if I throttle this boat to this throttling speed and I'm on a lake, the water isn't moving, I will move through the water at 4 meters per second. Okay? I will always call that the engine speed. I don't like to call it the boat speed because the speed of the boat depends on the engine speed and how fast the river is moving. The river's flowing west at 3 meters per second. What is the resultant velocity of the boat if it heads west? Okay, so what happens is, and I am not an artist, although that's a pretty nice looking river. We have a river, and the water in the river is flowing west at 3 meters per second. The boat is moving west through the water at 4 meters per second. I hope you understand this is the bug moving in the direction of the walkway. It's that simple. We're saying the resultant velocity, which can also be thought of as total velocity. What does total mean? It means add together. The resultant velocity, and I'm going to use vectors from now on, The actual result, what's actually going to happen to the boat, will be the sum of the engine velocity and the river velocity. So we need to add 4 meters per second east and 3 meters per second east. And I am sure many of you could have answered question A, not east, west. These are both west, am I right? Yeah. Okay, I apologize. These are both west. I'm sure many of you could have just looked at the question and said, well, the bug is walking west, the walkway is moving west, I need to add the numbers together. I know it's not a bug, but I'm just reverting back to that. So this works out to 7 meters per second west. What does this mean? It means if I gave you a problem in which the boat had to travel 4 kilometers downstream, how long would it take? You would use speed equals distance over time, but you would use this speed. On the other hand, in this situation, and whether you choose to draw these little sketches or not, I don't care. The river is flowing. Oh, and I drew them backwards too, didn't I? See, and then many of you didn't catch that. Let's fix that. One of these days I will fix that in my head. Again, I think it's because I'm facing you and you're facing me, and we're looking at maps and kind of mirror images. So these are both west. I apologize. So the river is flowing west at 3 meters per second, but the boat now is traveling east at 4 meters per second. Do you see that this is comparable to the bug walking opposite to the way the walkway is moving? So the result is, now I want to ask you a question. Is this, might as well. Is this true? No, it's not true. Is this true? Yes, it is true. Because when I put those vector symbols, I'm saying we're not going to add the numbers, we're going to add the vectors. And that means we have to add 4 meters per second east to 3 meters per second west. And if I had, forget about meters per second, if I had displacements and one was east and one was west, we've learned you subtract the numbers. So we get 1 meter per second east. Capiche? Okay. What if the boat points north? Well, listen, it's still that this is the case. The resulting motion of the boat is going to be determined by adding the engine velocity, what I call the engine velocity, to the river velocity. So we still have to add those things together. We still have to take the velocity of the engine, which is 4 meters per second, but in part C, the direction of that velocity is north, and add that to the velocity of the river, which is 3 meters per second west. Did I get my directions right, north and west?
Yes.
Okay. So how do we add these? They're not in the same direction. You don't just add them. Don't just add the numbers or the magnitudes. They're not in opposite directions, so you can't simply subtract those magnitudes. They're at right angles, so we can go ahead and create a right angle triangle, drawing west first and then north. So west at 3 meters per second, north at 4 meters per second. The resulting velocity will be this hypotenuse for the magnitude, and this angle for degrees north of west. I'm going to give everybody 1 minute to find both of those. How many of you know the hypotenuse of that by looking at the triangle? Okay, good. 3, 4, 5. Get used to seeing that as well, because it could be 6, 8. These numbers could be double, in which case the hypotenuse is not 5, it's double. So you are going to take, for the angle, I'm not going to explain the Pythagorean theorem, but for the angle, just in case, you're going to say tangent of that angle is equal to opposite, which is 4, over adjacent, which is 3. You're going to take the inverse tangent of 4 over 3 and get how many degrees to the nearest degree, Joseph?
53.
53? Okay. So this is the answer to the question. Are we still solid on this? Okay. So what's happening here, and I want to put this together so that you can see it for part C. The boat, much better than I could have ever drawn. The boat is traveling north and the river is flowing west. What we have done, and admittedly, I have drawn my vertical first, but that's only so it looks better on the diagram. Okay? It's so that I can label this in a different way. And please don't try to keep up and write all this down. I'm recording this. I'll put a link in our Google Meet or Google Classroom, and you can certainly take a look at it at your leisure when you need to. So every second that elapses, the boat is 4 meters closer to the shore in the north direction and 3 meters further downstream in the west direction. But the thing I want to really impress on you is the motion horizontally in the west direction and the motion vertically in the north direction are independent of each other. If we go back to the bug, remember when the bug was walking across the walkway and it took 20 seconds? How many seconds would it have taken if the walkway wasn't moving? 20 seconds. How many seconds would it have taken if the walkway was moving 3 times as fast? 20 seconds. The motion in that vertical direction for the bug doesn't depend on the motion horizontally of the walkway. And the motion of the boat doesn't depend on the motion of the river. The motion of the boat horizontally doesn't depend on the motion of the boat vertically. Okay? Because the river and the engine operate independently of each other. In other words, everybody, this statement, every second that elapses, the boat is 4 meters closer to the shore, would be true whether the river was flowing or not, whether it was flowing faster or slower. It's determined solely by the engine speed. So what's happening is this. 1 second goes by, and the tip of the boat went from here, to here. And it's traveled 4 meters north, and it's traveled 3 meters west. And that continues. It's traveling at 3 meters per second west. It is. But it's also traveling at 4 meters per second north. This is a huge idea to wrap your head around for the next few lessons with projectile motion. So, number 2, a motorboat with an engine speed of 20 meters per second heads east across a river flowing north at 5 meters per second. This is the final example, am I right? Okay. We're still good for time. What is the resultant velocity of the boat? Listen, some of you might want to find the resultant velocity without a diagram, but I think you need a diagram. We need to add, for the resultant velocity, we need to add the velocity of the engine and the velocity of the river. And I know that some of you will say, I know how to add this velocity and this velocity. How many of you feel as though you could add those velocities, not in your head, but without drawing anything? Okay. The caution I would have to you is don't screw up the angle. Because picturing where that angle is and what you do to get the angle is maybe a little bit complicated for some people. For those of you that are capable of grasping this, if you draw your horizontal first and your vertical second, your vertical is always opposite. So your angle will be 5 divided by 20 inverse tan, and it will be north of east. There are shortcuts you can take. But in order for us to add this as a group, we're going to draw a vector diagram. I'm going to pay extra careful attention to all of my directions from now on so I don't flip my east and west. This is 20 meters per second east. This is 5 meters per second north. These are meters per second, not meters. When we first did this a few days ago and we got to this point, I said you're going to be doing this set of calculations dozens of times. Physics 30, physics 20, all kinds of units. You should be able to look at this and find the sum of those two vectors pretty much on your calculator. I mean, if it's an assignment, I want to see work, but here you're going to use the Pythagorean theorem, and then you're going to use tangent to find the angle. Again, it's north of east because we drew the horizontal first. Did you get 21 for the hypotenuse? Don't worry about what I did. It's not important. I hope you understand. I'm going to write 21 because we're rounding to 2 digits, but it's a little bit more than 20. I mean, it's almost 20, right? Because the angle is so shallow. So 21 meters per second. And for the angle, we're going to take the inverse tangent of 5 divided by 20, which is a quarter, and I get 14 degrees. Good. Okay. How long does it take the boat to cross the river? Well, we're going to have to use speed equals distance over time. I'm going to go v velocity equals displacement over time. And the displacement across the river, are we told the width of the river? 80. That's 80. So I'm going to put into this formula, I don't like to work left to right, but I'm going to here. Don't go equals, just draw an arrow or something. I'm going to have the velocity equals 80 meters over the time. The question is which velocity? Because we actually have 3 velocities now, right? We have the engine velocity, we have the river velocity, and we have the resultant velocity. Which do you think we're going to use here, Noah?
Just the engine velocity.
Sorry?
Engine velocity.
The engine velocity of 20?
Yeah.
Can you tell me, this is meters. I'm just going to put in the units for this. We don't really need them. Why the engine velocity?
Because it's heading east and we're seeing how long it takes for it to get that way.
Good. So if we take a look at, and one thing that I haven't done here is drawn a diagram. The river is flowing north, right? So this is the river, and it's 80 meters across, right? And we know the boat heads across, but it's forced kind of in this direction at a very shallow angle. The point that's being made is this is still 20 meters per second east, and the boat has to travel 80 meters east. What I am getting at is that in this diagram, or this formula rather, these are both horizontal components. The 80 meters is a horizontal component of the boat's motion, so we better use the horizontal velocity of it. And that's a pretty easy calculation to make. I'm getting pretty easy calculation, and my brain screeched to a halt there. 4 seconds. I mean, 20 meters per second for a boat is really fast. It's like 80 kilometers per hour, roughly. How far downstream does the boat land? Well, this time what you're asked to find is a D. Remember up here, this D was a horizontal, but downstream, when you look at the diagram, downstream means vertically, because the boat is going to land up here someplace, and what you're asked to determine is that distance, which is a vertical or north component of the motion. So this is a y component. We want to find the time. We're still going to use speed, or velocity rather, equals displacement over time, but this time we need to use y components because the y component is what we're asked for. We're asked for how far downstream, which is the north component. So what happens is I put into this formula the velocity, which is a paltry 4 meters per second of the river. 5, thank you. 5 meters per second equals the answer to this question over the, wait a minute, we don't know the time. Do we know the time? It's 4 seconds. Remember, it's not 2 boats. If it took 4 seconds to cross the river, then it's been in the river for 4 seconds, moving 5 meters per second for those 4 seconds. So we use the same time. This is another issue that becomes very important for tomorrow and the next day. Even though we treat horizontal and vertical motion separately, they occur at the same time. So we cross multiply here and get 20 seconds. Are we okay with that? Sorry?
You're looking for displacement. You wrote the time.
Oh.
Time.
Thank you. We know the time is 4 seconds. Thank you, Christina. So we multiply those two and get 20 meters. Okay. So the answer to this question is it will be 20 meters downstream. All right. One final question. So on all of your exams, including the final exam, including every unit exam in Physics 20 and 30, including the diploma exam in Physics 30, you will have 2 numerical response questions that use this idea. If I go back and look at question 2, if I asked you, I gave you this information, and I did not ask you any of this, and I did not ask you any of this, I merely asked you how far downstream is the boat going to land, you would need to do part B to find out the time it crosses the river, and then you would need to do part C. Right? I've held your hand and led you down the path here, step by step. But that would be a good example of a numerical response question that I'm talking about, where you actually have to do some calculation first to do the calculation you're really after. I call it the 1-2 punch physics principle question. Okay? And by the time you get to Physics 30, these can be these are epic questions. They're massively difficult at times. They're really complex. This one's pretty easy. So in this question, what physics principle was used when we answered the horizontal aspect of its motion? If I go back and look at the horizontal, I want to reveal all this again. If I go back and look at the horizontal motion, I use this formula to analyze the horizontal motion. Are you with me? Okay. What physics principle allows me to do that? Well, this is the first time we've talked about this. You need to grab your formula sheet. There is a section on your formula sheet called Physics Principles. Okay. So we're talking here about using the formula velocity equals displacement over time. Well, I mean, I'm going to be sarcastic here. Do you believe that that formula is an application of conservation of charge? No, you don't even know what that is. That's Physics 30. What about, wave-particle duality? That sounds like a good thing. Obviously, we didn't use the concept of wave-particle duality. What we used, not these ones I'm highlighting, none of these, what we used is this. We used the concept of uniform motion. Okay? Because uniform motion means motion at a constant speed in a straight line, and horizontally speaking, that's what was happening to the boat. It was traveling horizontally, am I right in saying at 20 meters per second east? Okay, so we used physics principle 0. I want us to write uniform motion here. And then I'm just going to put 0 in brackets and I'll come back to that. I'm trying to teach you how to answer a typical exam question, and I haven't really arrived at it yet. When we analyzed the vertical motion of the boat, which was part C, did we still use uniform motion? Well, we still use speed equals distance at a time. The fact of the matter is the river is flowing at a constant speed in a straight line, so when you analyze the vertical motion, it's uniform motion. Which also, of course, is physics principle 0. So we're done with the lesson, okay? But let me explain the exam question as it would appear. You would see 2 numerical response questions. One would be, in this situation, how far downstream does the boat land? Not asking you anything else. Then the next question, and you will get used to this tomorrow especially, would be this. When you found out the distance downstream, you used 2 physics principles. What were the physics principles and in which order did you use them? So your first step involved physics principle 0. Your second step also involved physics principle 0. So that numerical response question would have this as an answer. I'll tell you right now that, you know, by the time you get to the end of this course, you're going to have sometimes 0, 1 as an answer. You'll do uniform motion first, then accelerated. Sometimes it will be 1, 0. Sometimes in this course it will be 5, 1. Sometimes it will be 2, 0, 2, 1. There's all kinds of combinations here. If your answer is 2, 1, that means you had to use uniform circular motion to get a number so that you could use accelerated motion to get the answer. So I wanted to throw that out and just get you used to that. There are some problems that I want you working on for tomorrow. You only have about 10 minutes, but I think the bug example made it a little bit easier. So get to work on those, please, and I will be around to check on you in just a minute. Yes? Mm-hmm.
Here, we don't need to write like if it's north because downstream.
You know, Christina has a really good question, you guys, and I should have twigged on that. So what we have done, I've got a slight error here, and you've seen it, but I want to really address it. What we have done is we have found a displacement. So the answer to this question is 20 meters north, right? However, well, the answer to what I have written is 20 meters north. How far means how many meters? So if you do see this on an exam and it just says how far downstream, yes, you use vectors to analyze it, but the answer to the question is merely 20 meters. Because how far means don't tell me the direction. Have I answered your question? Okay, good.